All right. Um, this is a bit of a response to Michael Penn's recent video about this exact same limit. So I remember doing this limit as an undergrad, and the professor kind of walked us through a specific uh, way to do this problem, and I think this is like a really beautiful way to do the problem. So let's start off by setting this limit equal to something. Suppose it exists. Say it's equal to y. Now, because we've got exponents here and factorials here, there's a lot of multiplication going on here. Um, I kind of hope to get rid of this nth root here. So one standard trick you can do is to take the logarithm of both sides. So we do that. And because the logarithm is a continuous function, we may bring the log inside of the limit. If we bring the log inside of the limit, well, let's see. The 1 over nth root can come out as a multiplier. What are we left with inside? Well, we have an n factorial on top, but we took out a 1 over n exponent here, which means this n down here did not have a 1 over n exponent. So to balance that out, we have to introduce an exponent of n. All right, so what do we have here? Well, if we write this again, and goes to infinity, we notice that here, this can be written as, well, let's see, n factorial is at the product 1 times 2 times 3, so on, until n. What is n to the n? Well, that's just the product, n times n times n, so on, n many times. So we see that for for every index 1, 2, 3, up until n, we can kind of pair these off. And by properties of the logarithm, we can turn this into a sum, right? We can write this as log of, well, 1 over n plus log of 2 over n plus so on log of n over n. But what is this? Well, let's write this as a sum, and let's bring the 1 over n inside. Our index here, let's call it k, starts at 1, goes up to n, and it's log of k over n times 1 over n. Now, this is where the magic happens. Our professor told us, well, have we ever seen anything like this before? This is a class that was taken after we had taken Cal 1, Cal 2, Cal 3. Um, so, a lot of students didn't get the hint. But if you do remember a little bit of Calc 1, you'll actually recognize that this is a Riemann sum, right? This 1 over n kind of is your delta x, and this log is like your function f at, taken at some point. And these points partition the interval. Well, let's see. 1 over n up till n over n. It looks like they go from the points 0 to 1, right? We have if n is big, then like 1 over n would be here. 2 over n would be here. And then, of course, n over n would actually be 1. So if you look at it as a Riemann sum, what happens when you take a Riemann sum, the number of partitions on the Riemann sum, and the delta x? Uh, what happens is that goes to infinity. Well, that actually just is exactly equal to the integral. Well, let's see, what's this integral over? It looks like we're integrating from 0 all the way to 1, our function here is just log x dx. And if we calculate that, you'll end up just getting a -1 because, well, I'll write down a little bit of the details. This is just nothing but x log x minus x, evaluator from 0 to 1. Plug in 1, we get a -1. Plug in 0, we get a -0. So this is just -1. So what do we get at the end? We end up getting that log of y equals -1, exponentiating both sides. The limit we're looking for is actually just e to the -1, which is exactly what we were looking for. Now this kind of trick where you take a really complicated looking, sum of a limit or limit of a sum, and you recognize it as a Riemann sum is really rare, and I've never really seen it in any other problems. This is one of the few problems where it really shows up, and it's a really cool approach.